All right, let's jump right into this explainer. Today, we're going to master the absolute secret weapon for carbon-carbon bond synthesis. If you've spent literally any time looking at organic chemistry, you know that building complex molecules is all about forging new carbon-carbon bonds. And to pull that off, well, you need a highly reactive nucleophilic carbon. So today, we are shining the spotlight on exactly that entity, the carbanion. Here is our roadmap for the day. First, we'll meet the carbanion. Second, we'll look at generating the intermediate. Third, we'll cover the rules of stability. And finally, section 4, we'll wrap up with reactions and rearrangements.
Okay, part 1. Meet the carbanion, anatomy of an intermediate.
So what is this thing exactly? At its core, a carbanion is a highly reactive intermediate featuring a trivalent carbon atom. That just means it's bonded to 3 other groups. But here is the kicker. It holds a negative charge and an unshared pair of electrons. Because it's got that unshared pair, it actually has a completely full octet in its outer shell. And that makes the carbanion exceptionally powerful, allowing it to act as both a really strong base and a completely potent nucleophile. To really wrap your head around this, we need to use what I like to call the rule of opposites. Basically, everything you likely already know about positive carbocations, just flip it. Flip it completely for our negative carbanion. Think about it. A carbocation is positive, it's electron deficient, and it acts as an electrophile. Our carbanion, on the other hand, is negatively charged, super electron rich, and it actively hunts for positive charges as a nucleophile. If you keep this mirror image concept in your back pocket, predicting their behavior is going to be so much easier. Now, experiments show that a simple carbanion actually prefers a pyramidal sp3 geometry. Why? Well, accommodating that unshared electron pair in an sp3 hybrid orbital is just way more energy efficient than sticking it into a higher energy, unhybridized p orbital. But here's the fun part. It doesn't just sit still. It rapidly inverts back and forth between 2 pyramidal forms. Honestly, picture an umbrella blowing completely inside out in a violent windstorm. That's exactly what it's doing. But here is where it gets absolutely wild. The energy barrier for this whole umbrella inversion is usually just 2 kilocalories per mole for a simple methyl carbanion. That means it flips constantly at room temperature, just all the time. However, if you swap out those hydrogens for fluorine, making a trifluoromethylcarbanion, that energy barrier mind-blowingly jumps to 120 kilocalories per mole. No way, right? The structure is essentially locked into place just because of that massive difference in the atomic makeup. Moving right along to section 2, generating the intermediate, the birth of a carbanion. So how do we actually make these things? There are 4 primary ways to, let's say, birth a carbanion. You can use a strong base to abstract a hydrogen. You can force a decarboxylation, add a nucleophile to an unsaturated compound, or just react an alkyl halide with a metal. And while these methods totally look different on the surface, they all fundamentally rely on heterolytic bond cleavage. Basically, the carbon atom is electronegative enough to just walk away with the entire electron pair. Let's look at the absolute simplest generation, direct heterolytic cleavage. Because carbon is more electronegative than whatever generic X group is attached to it, the bond breaks unevenly. Carbon keeps the electron pair, it gains that negative charge, and boom, it becomes a methanide ion. It is born entirely ready to react. Alternatively, we can use decarboxylation, and I love this. It's a fantastic synthetic trick. By shedding a very stable carbon dioxide molecule from a carboxylate ion, the remaining R group is basically forced into existence as a carbanion. It's the sheer stability of that leaving CO2 molecule that actively drives the birth of our highly reactive intermediate. Let's see how this actually plays out in the lab. By reacting a metal, like magnesium, with an alkyl halide and ether, we create the famous Grignard reagent. Because metals are vastly less electronegative than carbon, we create this Umpolung, or charge reversal. The carbon gets a partial negative charge. You've essentially transformed a carbon that used to be an electrophile into a hungry nucleophilic carbanion.
All right, section 3, the rules of stability, the survival guide.
Because these intermediates are so highly reactive, they're not exactly built to last. But let's look at the hard data. The stability of a carbanion directly depends on the strength of its conjugate acid. Look at these numbers for a second. Methane has a pKa of 44. That means it's a terrible acid, so its resulting carbanion is incredibly unstable. But look further down at acetylene at 25, or even better, that trifluoromethyl substituted molecule at an incredible pKa of 11. A lower pKa means a stronger acid, which yields a much more stable, far less basic carbanion. So what is actually driving these numbers down? First up is the S character of the carbon atom. Think back to your orbital shapes, right? The spherical s orbitals are physically much closer to the positively charged nucleus than those elongated p orbitals. Therefore, an sp hybridized carbon in an alkyne, which has 50% s character, holds that negative electron pair much tighter and much closer to the nucleus than an sp3 hybridized alkane, which only has 25% s character. And in chemistry, closer to the nucleus literally means more stable. Next up is the inductive effect. And hey, it's time to bring back our rule of opposites. We know that alkyl groups are electron donating. Now, for a positive carbocation, pushing more electrons towards it stabilizes it. But for a carbanion, it already has a negative charge, so pushing more electrons onto it is super destabilizing. Therefore, a simple methyl carbanion is the most stable, while a highly substituted tertiary carbanion is the absolute least stable. It is the exact reverse of carbocations. Finally, resonance provides ultimate stability by treating the negative charge like a literal hot potato. A localized negative charge stuck on one atom? That's high energy, uncomfortable. But if the carbanion is adjacent to a polarized multiple bond, like a carbonyl or a cyano group, those electrons can be delocalized. The more atoms that can share that negative hot potato across the molecule, the more comfortable and stable the carbanion becomes. Okay, section 4, reactions and rearrangements, the action phase. We know carbocations absolutely love to undergo these intricate rearrangements, just constantly shifting their atoms around to form more stable tertiary structures. But it begs the question, does our negative intermediate play by those exact same structural rules? Surprisingly, no. Standard 1,2 alkyl shifts directly from one carbon to another are practically non-existent in carbanions. And if you think about the mechanics, it makes sense. In a carbocation shift, a group migrates with its electron pair to fill a positive void. But in a carbanion, the adjacent carbon already has an unshared electron pair. The migrating group would have to move without its electron pair, which is incredibly difficult for an alkyl group to do between carbons, so it just doesn't happen. However, that doesn't mean they don't do anything cool. They absolutely participate in some highly specific, brilliant named reactions, like the Favre-Ski rearrangement. Picture this. An alpha haloketone gets treated with the base. The base steals a proton, forms a carbanion, and triggers this internal attack that kicks out the halogen. This forms a highly strained, three-membered cyclopropanone intermediate. Then a nucleophile cracks that ring wide open to finally yield a branched carboxylic acid derivative. It's this elegant molecular dance, and it's driven entirely by the carbanion. Similarly, check out the Stevens rearrangement. While carbon-to-carbon shifts are a no-go, shifts from a heteroatom, like nitrogen or sulfur, to a carbanion carbon absolutely do happen. In the Stevens rearrangement, a quaternary ammonium salt is treated with base. A proton is abstracted to form a stabilized carbanion right next to the nitrogen, creating an ylide. Then, an alkyl group migrates from the positive nitrogen directly to the negative carbon. This cleanly yields a new tertiary amine, and remarkably, it retains its absolute stereochemistry the whole time. And that brings us full circle for this explainer. By mastering the anatomy, generation, stability rules, and unique rearrangements of the carbanion, you hold the ultimate key to organic synthesis. You know exactly how to flip the script, create nucleophilic carbon, and forge the backbone of incredibly complex molecules. So I'll just leave you with this. What complex molecule are you going to build next?